In the last video, we debugged the BIOS and watched it jump away from the reset vector, initialize the floating point unit, and store the timestamp counter in 16-bit real mode. The objective of BIOS now is transitioning the CPU from real mode to protected mode. Let's open up Camo and GDB just like in the last video and continue where we left off. Here's some code that reads from an I/O port with the IN instruction. The I/O port number is CF9 and its value is being read to the 8-bit AL register. If we take a look at the chipset datasheet, we see that I/O address CF9 corresponds to the reset control register. Let's continue with reading. Now we have a conditional jump if the value we read was 4, but Camo gives us the value 0 here. I'm going to change the value in the AL register to 4 so that we enter this if statement. Let's continue and enter this branch. Now we see that we are writing 6 to the same I/O address, which is the reset control register, using the out instruction. Writing 6 here triggers a reset without power cycle according to the chipset datasheet. And sure enough, after executing the out instruction, we go inside the first instruction of the BIOS. Now let's go back and continue without intervening with registers. AL register is 0 again. This time I will leave it as it is. Now we are writing 1 to I/O address 80. This address is used for post codes. Post stands for power on self-test. It is a test routine carried out by firmware. Okay, now we are preparing for protected mode. We are loading the global descriptor table register with some value using the LGDTD instruction. The global descriptor table register is a 6-byte register in 32-bit mode. We are loading it with data in this address. So let's examine the value there. Here's the format for GDTR. First 2 bytes denotes the size of the global descriptor table, and the next 4 bytes denote the physical address the global descriptor table starts at. Note that the multi-byte structures are in little endian format. So with the data we have in this address, the global descriptor table would be 64 bytes in size and start from the address quadf FC40. We have +1 in size because 0 is not a valid size. So let's examine the 64 bytes at that address. These will be the 8 segment descriptors, since each segment descriptor is 8 bytes in size. The first one is the null entry, all zeros, and the others contain entries that describe their corresponding segments. At this point, we could examine each byte and try to understand which segment means what. But I have a simple parser, so let's feed this data to it and examine the output. Segments of interest here are the second and third ones. The second one is the code segment. The third one is the data segment. Note that both of them has base addresses of 0 and limits of 1 megabyte with granularity of 4 kilobytes, which makes the size come out to be 4 gigabyte. This is the maximum protected mode address space. So these segments map the physical space in identity fashion. After this, we enable protected mode enable and monitor coprocessor bits in control register 0. At this point, the next jump instruction would make the CPU enter protected mode. We then enable some SIMD floating point utilities in the control register 4. And now we are assigning 18 to all data segment selectors. 18 is the offset of the third segment selector, which we talked about, which holds a data segment descriptor. We are at the last 2 instructions before protected mode. So we are going to jump to an address. Which address, you might ask? Well, the address we will jump to is written in this address, quad F FC86. The syntax tells us that this is a pointer. If we examine the address quad F FC86, we would see the actual address we will jump to. So let's examine it. Here it says in the segment offset by 10 hex, which is the second segment, which was a code segment, the address quad F FA90. This is the address we will jump to. And sure enough, we jump to that address, and now we are officially in protected mode. Now my disassembly is bricked because it was configured for 16-bit code. So I need to fix my GDB arguments in the next video. So see you until then.